All right, let's do another CSES math problem, name game 2. As the title suggests, this is very similar to the previous video, name game 1. Again, we have n heaps, 2 players moving alternately, and every turn you pick a heap and remove some sticks, and if you remove the last stick in the last heap, you win the game. But instead of being able to move as many sticks as you want, you can only move 1, 2, or 3 sticks. And so the question is, who wins if both players play perfectly? Right, and you're just given some setup, right? Some number of heaps and some number of sticks in each heap. So in the last problem, the case of 1 heap was trivial because you could win instantly by moving everything. But here, 1 heap is actually not trivial. So let's look at that. So suppose there's just 1 heap. If it's size 1, 2, or 3, then you can just take everything and win. What if it's size 4? Then you actually lose because you can move, right? You take 1, 2, or 3 from it, which will leave it with 3, 2, or 1. And then the second player can take them all and win. So a size 4 heap, you actually lose. Because any move that you do, they can respond by taking it to size 0. A size 5 heap, you win again, because you can bring it down to size 4. In fact, 5, 6, or 7, you win. But 8, you lose again, because they can bring you down to size 4 in response, no matter what move you do. And so, in fact, that's the pattern for 1 heap. Right? Any multiple of 4 is losing, and anything else is winning. And it's maybe useful to say it's not just like losing, it's as though it doesn't exist. And in fact, that's always true for any losing part of a game, of an impartial game. And the point is that having a pile with 4 stones doesn't help you at all, because any move that you make in it, they can just respond by taking it to 0, and then you're back in the original position. So you might as well have just made a different move in the original position. Okay, and so actually any pile of, like all that matters in a pile is the number of sticks, sorry I'm saying stones instead of sticks here, the number of sticks mod 4, right? Because they can always, if you move in that pile, they can always respond by taking it down to just 1 less multiple of 4, right? Until there's no multiples of 4 left. Right, if the pile is 7 stones, that's basically the same as if the pile were 3 stones. With any move you make, they can bring it down to 3 stones. Right, any move that you make, they can respond by having the net effect of the 2 moves be to remove 4 stones from the pile. Right, 1, 2, and 3 pairs of 3, 2, 1. So effectively, we can actually reduce all the pile sizes mod 4, and now we're back to nim, right? Because nim is you can empty any pile in 1 move, and after you reduce all the pile sizes mod 4, then you can empty any pile in 1 move, right? Because you can remove 1, 2, or 3, which are all the possible pile sizes after you reduce mod 4. So the solution here is that we just take all the pile sizes, mod 4, XOR them together, and if it's 0, then that's a losing position, and otherwise it's a winning position, right? And that's just from the previous video. I'm not going to go through all of that again. Watch the previous video to understand why we do XOR. But this is why you can do mod 4, right? Is that any move that you make, they can respond, and the net effect of the moves is just moving 4 stones in the pile. So we can, any moves that you make in a pile with more than 4 stones, they can respond by having those 2 moves reduce that pile size by 4. And so all of those moves can basically be ignored, right? And if you just look at what's left after you sort of pair off moves like that, you'll see that you're just playing nim in with all the piles, mod 4. Okay, so that's enough to solve the problem. I want to talk about a more general way to solve problems like this. Right, this was kind of, I don't know, the like 4 thing was kind of ad hoc, right? We had to rely on the fact that we could like pair up the moves. Like if it had been 1, 2, and 4 instead of 1, 2, and 3, this kind of thing would not have worked. But there is actually a general solution, which is that any impartial game, right? We've talked so far about whether or not it's a losing or winning position. That's like 1 bit per position. But actually, a more productive way to think about it is to have an integer representing the value of a position. 0 means it's losing, and non-zero means it's winning, but there's different types of winning, right? nim pile of size 1 is winning, and a nim pile of size 2 is winning, but 1 and, 1, 1, if there's two piles of size 1 and 1, that's losing, and if there's two piles of size 1 and 2, that's actually winning. So tracking the integer instead of just tracking the bit, or a Boolean, lets us combine games. And the way that we can combine games, if we have these integers, is with XOR, right? Just like in nim. So effectively, the claim here is that any game is equivalent to nim with some, one heap. And actually, that's true of nim itself, right? You can combine all the heaps together with XOR, and it's effectively the same game as though you just had one heap of the sort of XOR together size, which would be useful if you wanted to then combine, say, your nim game with some other game. So how do you compute the nim value of a game? The nim value is the max of the nim values of all of the positions that you can move to. So max is a function, which I'm about to tell you about, that takes a list and returns an integer, right? It takes the list of the nim values of the positions you can move to, and it gives you back your nim value. And max stands for minimum excluded outcome. So it's the first number that doesn't appear in the list, starting with 0. So for example, the max of 1, 2, and 3 is 0, because 0 is not in this list. But the max of 0, 2, and 1 is 3, because 0, 1, and 2 are all in this list. 3 is the first element that's not. If we have like a 5 or something, it would still be 3, because anything bigger than the minimum excluded value doesn't matter. So let's see how to compute the nim values for our game. So let f of n be the nim value of a pile of size n. And because of the rules of the game, you can remove 1, 2, or 3 stones. We know that this recurrence is true, right? F of n is the max of what you get if you remove 1, what you get if you remove 2, what you get if you remove 3, right? Those are 3 moves, so we're taking a max of 3 things for any position. And so we can just sort of write those values down, right? Well, for 0, there's no moves, so the max of the empty list is just 0, right? That's the first number that's not in the empty list. For 1, you can only move to 0, so the max of just 0 is 1. For 2, you can move to 0 or 1, so the max of 0 and 1 is 2. For 3, well, the max of 2 and 1 is 0 is 3. But for 4, something interesting happens, right? Because our only moves are n minus 1, n minus 2, n minus 3, so it's the max of 3, 2, and 1. And so f of 4 is actually 0, right? The nim value for 4 stones is 0, right? Which is what we talked about above. And so the point is that with 4, there's no way to move to a losing position, to a position of value 0. And so 4 is itself a losing position. Right? That's a way of thinking about max, is that, right, or you can see that max preserves the, a position is winning if and only if you can move to a losing position. Because the max is going to be non-zero if and only if one of these successors is 0. So max gives you, the nim value is a little bit more finely grained to that. You can say how much you're winning in a position, right? If you can only move to 0, then you have a max of 1. But if you can move to 0 and 1, then you have a max of 2. So 2 is more winning, maybe, kind of. So anyway, f of 4 is 0. It's a losing position. F of 5 is just the max of 0, 3, and 2, which is 1. Right? There's no 1 there. F of 6 is the max of 1, 0, and 3, which is 2. F of 7 is the max of 2, 1, and 0, which is 3. And f of 8 is the max of 3, 2, and 1, which is 0 again. And so we can see that this system is reproducing the results that we got before, where any multiple of 4 doesn't matter. And so actually we can see that f of n is n mod 4. And then, so to compute the nim value of the entire position, we compute the nim values of each of the heaps, which is just reducing the mod 4, and then we XOR them together. So this is the same solution as we got before, which should be, because that's the right answer, but in a more general way. Unfortunately, they set the bounds on this problem to the heap sizes of up to a billion, so we can't actually compute this with the recurrence. right? Because we can't really run like a billion steps of this. So we actually do have to spot this pattern, right? You can't just sort of brute force this problem with a general solution. But this is like a good thing to know. And if it had been 1, 2, and 4 instead of 1, 2, and 3, then this is probably the best solution. Or maybe there's still a pattern, I'm not sure. Probably is. But a more complicated sort of version of this, you'd wanna use this instead of this sort of ad hoc reasoning up here. So yeah, I'm not gonna prove these facts. I'm just gonna, you'll have to take it on faith or look it up yourself if you want. But they are true, and this is like a general way of approaching impartial games. It's very, very important to do. And this is called a Sprague-Grundy. I'll link that in the video. Okay, so we did a lot of talking, as usual with these math problems. Let's code it up, and we'll find the coding is rather easy. It is in fact just the same as the previous problem, except that you take the file size as 1/4. So we do the number of cases, we do the number of files. Right, take it mod 4, XOR with the answer. And we're supposed to print out second and first. Okay, so this should be first, second. First, second. Cool. Okay, so that worked. As usual with these harder math problems, the coding is short, but the argument is longer than the code. Right, so we talked about 2 ways of thinking about this. One is this sort of ad hoc solution where we notice that multiples of 4 are special, and that they might as well not exist. And then notice that once you reduce everything mod 4, we're back to the original rules of NIM, because any pile can be empty, and this gives us the solution. And we also talked about this more general solution using Grundy numbers or NIM values with max, which allowed us, it's a more systematic way basically of observing the same pattern, which is that all the pile sizes mod 4 are 0, or losing positions, and in general, the NIM value of a pile size n is just n mod 4. So either way, we get the same solution, which is identical to the previous problem, except for this line. So that's the problem.